So this is a video to just demonstrate the different ways of representing a function. The verbal description was already mentioned in the PowerPoint slideshow, so I will go to a mapping. In a mapping, we simply have a list of the input values and a list of the output values, whatever they may be. And quite literally, the relationship between the input and the outputs is represented by nothing more than an arrow indicating which input produces which output. And this is done all the way down the line. Now, we may not know the relationship between them, what the rhyme or reason is. In this case, it would be impossible to define it mathematically because the input values are not numerical. So mappings can be useful if the list of inputs and the list of outputs are not terribly long, and particularly if they are non-numerical, because an equation would not suffice then. This relation represents a function. Now, the definition of function, recall, is that each input produces only one output, or is paired with only one output. That means that if we go down the line and we say the input is A, there should only be one output to go with it. If the input is B, there is only one output to go with it, and so on and so forth. Now, note here that A produces an output of 2, and E is also paired with an output of 2. This is okay. The definition of function does not place any restriction on the outputs and how often they may be produced or paired, but the inputs may only be used once. As a counterexample, this is another mapping, but this time it will not be a function. So again, without needing to know what is causing each input to be produced or to be paired with each output, what we have here is a relation that is not a function. In this case, again, if we go down the list from the beginning, the input of A does produce a single output. Where we run into trouble is with the input value B. The input value B produces more than one output, or is paired with the outputs 3 and 4. Now, as it turns out, we also have an issue with D, which produces or is paired with the outputs 2 and 3. Now, A and C conform to the rule, and that's fine, but B kind of ruins it, so does D. It only takes one, but in either case, this then is not a function. It is a relation, but it is not a function. Now again, mappings are not used terribly often in math. There are much more efficient ways of representing relations in math, but they do serve a purpose, particularly when, again, the list of inputs or outputs is relatively short. The rule is not necessarily known, but we do know the pairs, and particularly when either the inputs or the outputs is not numerical. The next type of representation then is a table of values. A table of values is something you would be much more likely to be familiar with. You see them fairly often in math when dealing with two variable relationships. Now, one of the advantages of the mapping is that we do not need to worry about the order in which the inputs or outputs are listed because they are connected by arrows. So as long as the arrow is there, it doesn't really matter where the input is and where the output is, as long as the arrow connects them. In a table of values, we are a little bit more restricted because it does matter because the input and output pairs are right next to each other. So the input -2 is paired with the output 4. The input -1 is paired with the output +1, and so on. We often will see these written with X for the input and Y for the output. Those are the traditional variable choices. Other letters can be used depending on the situation, but if we don't have a context, we don't have anything to suggest other letters, we just use X for input and Y for output. Once again, this is a function provided each input value is paired with only one output value. Since in this case, the relationship is direct, the connection is direct, whenever we see the input value appear more than once, it means that it is being paired with more than one output value. That does not happen here. Each input value shows up exactly one time. So if you know that the input value is, say, -1, there is no question. The output value is 1. If you know that the input value is 2, there is no question. The output value is 4. Once again, we see that output values may be included in more than one pair, but input values cannot. Now, again, relations, there are many relations between sets of inputs and outputs, but those relations do not all need to be functions, even when they are numerical. Here's an example of a relation that is numerical, and in a table of values, but is not a function. Again, the input value of 7 is paired with the output value -1, and so on down the line. But we don't know the equation that relates these. We don't know what the rhyme or reason is, but we do know that there are input and output pairs. And if we look at the list, we see that the input of 5 has 2 different output values that it is paired with. That's all that it takes to ruin the definition of a function. As it turns out, we do have a second rule breaker there, but it is still a relation. Now, one of the advantages of tables over mappings is that even if we don't understand exactly the rule that connects input value to output value, we can, if we can see the patterns, extend them. For example, it's not too hard to see that the input values are counting up by 1s, which means the next input value in the table could be 4. The outputs are perhaps a little bit less obvious, at least at first, but from here on down we might recognize those as the perfect squares. So if we know the next perfect square after 9, that would be the next output value. So tables can be extended downward, or even, if we have the room, upward in the other direction, even perhaps filling in some of the values in between, although that can often become a little bit trickier because we'd have to go to fractions. But it can be done. Even in something that is not a function, we can still extend it if we know the pattern. Here, it's the output values that count up by ones. So the next output value might be 5. The inputs are perhaps less straightforward, but after 5, it seems we're going by odd numbers. The next input value could be 7. So we can again extend the pattern for something, whether it is a function or not, as long as we can ascertain the pattern. Now, the next and the most common by far way of representing a relationship, in math at least, is with a formula. Many times we actually start with a formula and then have to ascertain characteristics of the pattern from that. And sometimes we have a table of values or a graph and we need to determine the formula from that. Formulas are any type of equation that relates a variable for the input and a variable for the output. Again, typically x for input and y for output. Another example might be something like this. Now, formulas make it much more difficult to tell when something's a function just at a quick glance. But as it turns out, there is a rule. If we are treating y as our output value, then what we would like to see is y a function of x? This phrase is used to indicate which variable serves as the input and which serves as the output. In this phrase, when we are told function of x, or whatever other variable we're using, the variable that we are looking at a function of is the input, which makes this variable here the output. If y is a function of x, if a single value of x can be put in and we can produce an output value from that, then we should be able to write the equation as being solved for y. This is a linear equation, something that you would have seen in previous courses and should be fairly familiar with. If we were to solve that formula for y, this is also known as writing it in slope-intercept form, we would get y equals negative 3/4 x plus 2. This here, y, is an expression entirely in terms of x. That's the key to being a function. We should be able to get y by itself, and on the other side have an expression entirely in terms of x, or whatever input and output variables are that we're using. This is a little trickier. I'm not going to take, again, like the slope-intercept form, I'm not going to go through all the steps of it, but in order to get y by itself, we would eventually need to use a square root to undo the square. And if you remember solving quadratic equations, this results in a plus or a minus. So what we actually get from this is y equals the square root of 1 minus x squared, or y equals negative the square root of 1 minus x squared. This prevents this relation from being a function because I can take the same x value, put it into both formulas, and I will get two different answers because the formulas are virtually identical except that one is positive and one is negative. So whatever y value I get for one, I will get the opposite y value for the other. Therefore, the same x producing more than one y. So while it seems like we can solve this for y, there's a hiccup. We need something that is clean and clearly defined, a single equation solved for y in terms of x. Formulas are far and away the most common representation of functions that we will see, and as such, they have their own special notation. And that will be covered in the next slide of the PowerPoint.